Hello, this is a Patreon-only video. We're going to talk about the back of the napkin, the BON of the Rowland experiment, which we kind of touched on a little bit at the end of last week. Okay, in this video, we're going to go over the theory of the Rowland experiment and how we're going to use it for ethereal mechanics. And then we're going to do a back of the napkins calculation. And we're going to show you from the back of the napkins calculation that it isn't really going to work for our purposes in its existing form. So we're going to show the path forward, and then we're going to give a quick status of the other experiments. So what we have, this is online animation here. And if you go to this website, what it shows you, if you click the button, you'll see the charge disk spin and it'll deflect the needle. And then you have to hit pause before you can make the charge disk spin in the other direction. You'll see that the compass needle deflect the other way. That is the Rowland experiment, which shows that charges in motion create a magnetic field. And this is what ethereal mechanics says. But in ethereal mechanics, it's the charge motion relative to the medium is what causes it. Okay, and so where we wanted to go with this is we want to take a disc with some copper plates in it that are going to be charged. Now, what I'm showing here is it's figurative only, because in reality, if we make this disc, which we just might, is we would have the sectors as little sectors around the edge of the wheel. Okay, it's just easier to draw this. So this is figurative right here. So the idea being that we charge up these plates with a certain amount of voltage, which will put a certain amount of charge on them. And then we spin this disc in one direction. If we're spinning it up on this side into the downflowing ether, because the ether, according to ethereal mechanics, should be flowing earthward at 11,000 meters per second. Okay, if these plates are spinning into the ether, we're going to see a stronger magnetic field. And if we change the direction of the wheel, okay, where the wheel is now moving with the ether, we should see a much lower magnetic sensor reading. Okay, and so let's do a back of the napkin calculation and see, how big a wheel do we need? How fast does it have to spin? And what kind of sensor do we need to make a realistic measurement of this effect? Okay, so we're going to start with the hard limitations that we have. And the two hard is the size of the disc that we're going to produce and the magnetic sensor, misspelling, sorry. So if we're going to make a disc, we're most likely going to make it from a printed circuit board, have it made, and you want to do the cheap DigiKey red thing here, and their max board size is 10 by 10. So the biggest wheel we're going to get is going to be 10 inches in diameter, which is probably of the big sizes that you're going to get for most of the houses anyway. And they're cheap and fast, the DigiKey is, for 2 and 4 layer printed circuit boards. Okay, so that's one of the hard limitations that we're going to have, is the size of the disc. And the other hard limitation is what's the most sensitive. This is a list, a printout of our sensors in stock. And these are pretty current with what's available. And the most sensitive one we have here, when you look in terms of noise, is a 5983. And we have those both in module form, and we have them in integrated circuit form. And they could do 0.4 milligauss, which is 40 nanotesla. Now that's the noise. That's the noise floor. In reality, the A to D converter can go down to 3 nanoteslas, which is like a factor of 10 smaller, but that's still below the noise floor. We could get there, but we'd have to average up a lot of samples to get there. So let's just stick with 40 nanoteslas as the ballpark of what we're looking for as far as the field we're trying to measure, with knowing that we can go below that if we need to a little bit. Okay, so here we're going to make a disc, which again, it's not going to have this sector configuration. It's going to have something more along the line, of sectors along the edge. Okay, and what we're going to have here is we're going to have discs in motion. These are capacitive plates. Okay, so the effective current of this wheel, the effective current is going to be the charge on each little sector times the tangential velocity of the wheel. The tangential velocity of the wheel is the turns per second times 2 pi r. And the charge per sector is the voltage that we're going to put across. We'll show you in a moment how we're going to do that. and then the capacitance, the coupling that's going to be there. These are in blue because they're legacy units. This is volts and this is capacitance. These cancel, which gives us charge. Okay, and the capacitance, okay, distinguish, this is capacitance, is lowercase c is speed of light. Uppercase C is capacitance, lowercase c is speed of light. So the capacitance is going to be epsilon naught times the area of the capacitive plate divided by the distance between them. Because what we're going to do is over on this side, we're going to have another stationary capacitive plate. So as the sectors pass that plate is going to be charged to, let's say, positive 5,000 volts. And then the sectors, there's going to be a brush touching this sector to ground, which is going to allow negative charge to seep onto this plate. And then as the plate passes off, it's going to carry the charge with it. And as the next plate goes in that stationary capacitive plate, it's going to charge. And that's how we're going to basically charge it over here. And then so we're going to have charged disks spinning around. And every time they pass this point, they're going to get recharged back up to 5,000 volts. Okay, so effectively, when you put all this stuff together, the effective current of this wheel is going to be this equation here. And then, to know what the magnetic field of that is, well, there's an online equation here for, what is the magnetic field about a loop. Okay, and so I've reworked it for this. But what I've done instead is this x here is the distance from the center of the wheel to the sensor, but we're going to change that to the radius plus a little distance thing here. So I'll rework that. Now, if we work this, put all the values and all the equations into a spreadsheet, okay, this is what the spreadsheet says. Okay, up here is our minimum detectable field, which is 40 nanoteslas. And we're starting this at 4 turns per second. The yellow are the input fields. The blue are the conversions to metric for the equations. The green are the computed results. So down here, we're looking at, if we're doing it 4 turns per second with a 5-inch wheel, with each one of the plates having 1 square inch of area, and we're separating the charge plates from the charging plate by a 1/16 of an inch. Okay, and the sensor distance we're going to make is a 1/2 inch away from the edge of the wheel. And so the magnetic field at the sensor from this configuration is going to be 8 times 10 to the minus 14 teslas. Okay, this is effectively 2 million times smaller than what we can measure. Okay, so we have a situation here. Okay, now, I mean, we can go and we can change the voltage to 50,000 volts to get a factor of 10 there. We can turn this maybe 12 turns per second, maybe 40 turns per second, but that's, 50,000 volts is going to be a lot more equipment that we don't have, that we're going to have to go scout out and purchase to get the speed up to 40 turns per second. We're going to have to get something other than stepper motors to do that, and then some means of regulating that speed. So if we're going outside, I mean, the best we can do with our existing stuff is 12 turns per second with stepper motors. Okay, that's only like a factor of 3 there. All right, and that only gets us to, it moves us up a little bit. So yeah, we could play with these parameters and move this value up to the point where we could measure it with our detector. Okay, but we're talking, that's going to be a much more complicated experiment than I want to run. Okay, so let me just go to the next page to show you where we're going with this. Okay, so what I've done, as you saw, I spent time massaging the parameters. It's possible to obtain measurable effects, but we'd need major equipment upgrades in terms of voltage, motor speeds, maybe go to a bigger size wheel. However, in doing that, I stumbled upon a realization, is that we're trying to detect the earthward flow of the ether, which runs at 11,000 meters per second. Okay, at 12 turns per second, okay, the edge of the wheel is only moving at 9.5 meters per second. So it's like 1,000 times smaller. The speed of the wheel at our current equipment level is 1,000 times smaller than the actual motion of the ether. So the rotation of our wheel is kind of insignificant to what we're measuring. So let's not even consider the rotation of the wheel. Let's do this instead. Okay, let's instead, I just said that. Let's instead just take a charged disc, okay, that's effectively moving upward at 11,000 meters per second, a half an inch away from a sensor. And we can work out all the equations here. I'm not going to work them out for you, but if somebody wants to go and check these for me, please do. And that works out that just using plain old Biot-Savart, that the B field at this sensor, okay, we're going to put this into the equation here, works out to, we're not using the wheel here, so that goes away. That's not part of our equation. Oh no, we are using the wheel. I'll show you why we're going to still use the wheel. But essentially now, if we just consider the motion of the charged plate through the medium, that's going to get us a measurement that's about 3 times more powerful than what our 3 times more than what we can measure with our detector, which is good. It means this experiment is doable without major upgrades of our equipment. I mean, there are probably some pitfalls we have to think about where people could say, "Oh, you know, you're measuring that measurement because of this, that, the other thing." I think I already know how to weave around all that, but I'm not going to worry about that right this moment. Okay, so what we're going to do, the way we're going to do this experiment, because we still need to get a charged disk or a charged sphere or some kind of charged conductive object next to the sensor. Okay, so what we're going to do is still use a wheel, but use the wheel that's spinning in the horizontal plane. Okay, so over here we'll have a 5,000 volt voltage generator, and there's going to be a capacitive plate that as the wheel is spinning, the plate is going to come in contact with a brush opposite the stationary plate that's connected to the other side of the generator. And that'll impart the charge on this disc. And as the wheel moves off, the next wheel will come in. So the purpose of this is to keep these plates continually charged. So when they move out here, they should be well charged so the sensor can detect them. And because we got more than one plate in the vicinity of the sensor, we should get even a higher magnetic field measurement. Okay, so we still need some kind of charge transport device. I was even thinking of a small Van de Graaff generator, but it's a lot easier to do this charge transport with charged conductors rather than with a rubber band belt like a Van de Graaff uses. At least if somebody has more experience and knows something better, please tell me. Okay, so that's where we're going to go with this. This looks like a pretty feasible experiment. And one of the other ideas would be is to have an arrangement here that charges alternating disks, positive and negative. So that would give us a square wave, or it would probably make a triangle wave going by the sensor, which would give us the two-directional thing we're looking for. Because we kind of need to make it work in both directions. Okay, because somebody could say, "Oh, you just have drift or you just have bias." And this way here, if we can show that alternating charge on those plates gives us equal and opposite measurements on the sensor, that would be, I think, a very clear and hard to disprove experiment. Okay, so let me give you the quick status on the other things going on. The Galaxy Simulator, today, an hour ago, the polypropylene ball bearings came in, tested them out. They do float. They work great. I ordered with the smallest ones I can find. They're probably actually too small, so I have to order some larger size balls. The CRIM, we're done with the scope and the arbitrary waveform generator drivers. And when I was developing the calibration procedure, I realized that we should use a precision DMM to calibrate this. So I have to now start the precision DMM drivers. Okay, and right now we're very close to being done with this. We're like in the home run with this. So what I'm going to do is, other than ordering parts and stuff like that, I'm going to put all other efforts on hold because I want to get the CRIM done before my summer vacation, which starts the last week of June, first week of July. Okay, so that we can start. I want to put all my summer vacation into the Galaxy Simulator, and then we'll go on to the Rowland experiment after that. Anyway, thank you all. Thank you for the patience from my Patreon folks. You guys are great, and I'll talk to you again next week. Thank you.